All good. Thank you. Okay, good morning, everyone. Okay, so I added two PDFs to the Canvas. So the first one, just kind of go through what you were asking for, about the convolution details, so a few pages there. And then today we'll talk about architecture for different CNNs. So this is a survey paper, all the different architectures, so we talk about in more detail. So this one, the first one, about convolution, it really goes through much more detail than what I covered last time, but it's nothing really new. So for those who already forgot about the convolution, this is a very good refresher. And then the second one is a survey paper. Throughout today's lecture, I will be citing this paper. So I really strongly recommend that you read this paper. It will really help you understand the different architectures. It's a survey paper, so it's very, very long paper. So this is kind of the two things that I added to yes. Yeah, that's a survey paper, a double space. Here it is. Not bad. It's a very easy read. And most of you will see basically the architecture I will be covering in detail will be very obvious what I'm focusing on, but there will be some other architecture like the Inception one from Google. I don't really cover them in detail because I don't like them. So there are quite a bit of pages there that you don't have to read through. So, but everything else is very, very helpful to read. Yes. For the project. Any of these just kind of. I will address that. I plan to address that after I finish talking about architecture today. Before I talk about the training, there is a summary. I will talk about that specific point. All right. Okay. So we'll continue doing our CNN. So today, mainly the core of it is really to cover different architectures, and then we cannot really go through all the different architectures out there, but we are really picking the fundamental ones. And then not necessarily just to show you what they look like, but also there are some tricks how you train. So the like dropout, for example, normalization, what are the different tricks they use to build this architecture. And that's actually what we are really trying to focus on today. And then I will start a little bit to talk about the training of CNN, and then we'll continue on Wednesday with the training. Okay, so this is just a recap from last time. So we have an input on the left-hand side. And then we have six different filters, 6 different kernels, whatever you want to call them. And then the output on the right-hand side will be maps. So we call them feature maps or activation maps. They will highlight basically certain content in the input image. And that's basically what the convolution between each one of these filters and the input on the left will produce a single map on the right-hand side. We talk about the receptive field. Remember, the CNN basically was really motivated from the image side of things, the vision side of things, so receptive field. So for these 3 layers in here, this is the input layer, so it's not really a convolution layer. And then you have layer 2, you have layer 3. Then every single basically point or data point or pixel in layer 3 has a perception field of 5 by 5 if you are using a 3 by 3 filters, right? If you go to 3 convolution layers, then it will have what, 7 by 7, right? So each pixel in layer 3 of the convolution, or layer 4 in the network, it will have a receptive field of 7 by 7. So this will become handy when you design architectures. If you ever in your job design architecture to say, basically, do I want to have smaller kernels, right? Or I want to like smaller kernels with multiple of them, or I want to have a single kernel really very large, right? So these are the 2 different strategy in designing your architecture. We'll talk about that more. I'll talk about AlexNet and ResNet. Okay. Okay, can you repeat the question? Just tell me if I got your question correct. So as you go deeper into the network, the receptive field give you information about what the network is seeing in the data, or is just just math, right? Is that what it is? Mhm. Okay, that's a very good question. When we talk about visualization and interpretation of CNN network, like explainability later on, and I'm hoping that Mohit Prabhashankar, he will come here and talk about that. So early in the network, you will start to make sense of a lot of things like edges, like you see like the color. So the filters are really doing color and edges, for example, for the images, right? Or some other frequency components, right? As you go deeper and deeper, every single one of those maps is very, very sparse, like extremely sparse. So you don't really have, it's mainly zeros, very little basically here and there. Collectively, we cover the context, right? Together with the remaining layers. So if you just take one map, it will not make much sense. You will not really get something really very useful as you go much deeper into the network, right? But collectively, there are some tricks how you can really get some information. And we'll talk about that in visualization and explainability. We'll talk about the GradCam, GradCon, and these different techniques to do that. So you have to do processing on those maps to make sense of them, right? And we'll talk about that. I'm a big fan of saying the activation maps or the responses, which these ones on the right-hand side, these by themselves don't really give you the full picture. They are only an instant, capture of what the network is doing. If you really want to understand what's really happening, you have to look, because at the end of the day, the map is the network is creating this basically space where the data is relied. So you are constructing that space, right? And now the main component in constructing this space is the gradients. So if you have an idea about the gradients, how the gradients behave, how the network shifts the space from one to the next, from one iteration to the next, from one data point to another data point, right? Then you have a much better information about what's really happening. And that's basically part of, we will have a chance to share some of our research in that area to show you what gradients are much, much more insightful than just looking at the feature maps. The feature map is very, is like taking a screenshot, right, of something that's much more complex. So a screenshot just tell you one part of the story. It doesn't tell you the whole story. The gradient tell you much more. It doesn't really tell you the whole story or not. One of my postdocs, basically, Mohit, he has a mathematical proof that it does. And we can talk about his paper later on in the semester. We'll talk about explainability. Okay. So we did this specifically kind of pooling layer, right? I mean, to really reduce the number of computation that we have. And we have different pooling, max, average, L2 pool, and more, actually. And then we talked about kind of putting everything together as a network. So you have the input, you have the convolution, you have the activation layers, you have pooling, and then you keep basically stacking them. You end up with a fully connected layer at the output. And then the final, fully connected layer, and here kind of the softmax if you have a multi-class classification, where the number of basically output in here is equal to the number of classes that you have. Okay, so let's talk about architecture. So this is kind of a timeline of the different architecture. You can see Linnet, he used to be a professor in NYU, but now he's the head of FAIR at Facebook. That's basically his network from 1998. And then you can see there is a huge gap until we got things running again, like in 2014, 2012 timeframe. It's not the first neural network. Neural network really showed up in the early 80s, like 1981, 82. You'll have some papers there talking about neural networks. It is the University of Tokyo in Japan, actually one of the earliest paper about neural network from 1981. But the whole fully connected layer, everything is there. What they were missing basically at the time, data, right? And GPUs, right? So, but mathematically they had everything laid out since then. And then Yukon came and he kind of implemented it on MNIST, and it really worked. So it literally implemented the 1981 work, but with extra layers. But then we had quite a bit of a sleeping, stage, because the hardware is not there to scale it up, and the data is not there, right? So basically, thanks to all the population online with all the YouTube clicks, so now we have we have data, right? They have been collecting our data for a long time. So we have quite a bit of very crowded, basically, the last 8-9 years, number of architectures. We will not really talk about all of them. We'll talk about AlexNet because I think is extremely important one. AlexNet, VGG, and then ResNet. So these are the ones I will focus on. I will just mention very quickly the Inception V1 all the way to V3 from Google. Have Inception, but I'll really focus on these concepts: AlexNet, VGG, and ResNet, and what are the different things that they managed to train, because they have different strategies. So this is kind of, I think I talked to, Cooper about the legend. There's a very confusing legend. So this is really kind of really literally a screenshot of what the agreed upon legend for your network. It's not necessarily everybody is following it, but at least in this lecture, hopefully we'll stick to this as much as we can. So what we have in red, we have a convolution operation. So this will tell you basically, is it 3 by 3 or is it 11 by 11 or 5 by 5 and so on. And then in gray, we have the pooling and tell you basically average pooling, what the dimension of it. And then here we have what you were asking about, Cooper, basically the concatenation, right? So we have it in purple in here. Either you are really adding, you are concatenating, you are just, we could just call them merge, right? So, and it can be very different. So it can be adding, can be concatenation. It depends on what the network is really doing at that stage. And then we have this blue layers in here, which is the dense layer. This is really nothing but a fully connected layer. This is a fully connected layer. Everything from the previous layer is connected to every single neuron in this layer, right? So this is a fully connected layer in the blue in here. And then we have circles in here for activation function and for some other kind of function that we will talk about. So for the activation function, we have them in yellow. So we have the hyperbolic tangent in here, and we have the ReLU in R. So we have T and R in here. If you have an S with yellow, basically we have sigmoid. Then we have B with the white background as a batch normalization, and then we have an S with a white background as a softmax operation. You'll see basically because very, very deep layer, deep networks. So sometimes we'll have to put things into a module. So you'll have a module A that has really a convolution layer followed by a pooling layer. Module B could be a convolution layer followed by another kind of pooling, and so on. So we will have quite a bit of these kind of modules as we go to the ResNet, like 152, for example, later on. And then you will see this very common, not in AlexNet, but later on in ResNet, we will see this. And this means basically I'm repeating this twice, right? So this basically I'm repeating this twice. We just not enough space on the paper to put all of this. Okay. So the first one is LeanIt from the, as I mentioned, the late 90s paper. And what we have in here is really kind of, we'll talk about the contribution, what really added to the field. But you can look in here, we have the input, the 32 by 32, a single channel. So this is a grayscale. It was tested on the MNEST dataset, and the MNEST basically at the time, it was a 95% error rate, or 0.95% error rate for the top 5 error, right? I think the top one, I forgot the top one, yes. We'll talk about those basically as we go in the details, but I will talk about it. Basically, the difference between it's give you -1 and -1 is the same shape as sigmoid, not 0 and 1, right? So basically, that's the main motivation. But there are some other papers where they just do the sigmoid and the performance is very close, so it's not really a big difference. But we'll talk the difference between ReLU and hyperbolic tangent, for example, in a few minutes. So this is really a 5 by 5 convolution layer followed by the hyperbolic tangent activation function, average pooling of size 2 by 2, and then we repeat that again. So this is basically just a repetition. So we have 2 convolution layer in here, and then we have one fully connected layer, another fully connected layer, and then here we have the final basically connected layer of the softmax. And basically we have the 10 neurons in here because we have 10 digits, right? 0 to 9. That's why we have a 10 here. So we have 1, 2, 3, 4, 5. So this is 5 layers that we have in this network. So in here, the main contribution here is basically it proved that we can have an end-to-end, meaning that I really don't, because before this paper, people were having a neural network, but they will feed to it a feature. So we'll say, okay, I will create the sift features. I will create, Fourier transform features. I will create some kind of features. I don't know about the data. Like for example, for MNIST, I will just create edges and then, curvature. These are my features. I engineer my features. I input them. So this one showed, that was really the main contribution of this paper, that you can really input raw data and then let the network learn these features. So you really don't need to do engineering for those features. That's really the main contribution here. Yes. Okay, so the question is, do you need to do any pre-processing on the data, or you just trust the network will do? It depends on what you are referring to pre-processing, right? So if it's just raw data like this one, there's no noise distortion issues, then you just feed it and let the network will handle creating the features, right? So that's the one. But if you have some kind of other task, like you want to denoise, you know there's something, the data has something wrong with it, you want to register it, you want to align it, you want to do different things, then you have to do pre-processing beforehand, right? But now, it's very, very important to understand what the pre-processing has an impact on the whole thing, because I have seen, for example, when you do video, right? When you do video, you have the raw frames, right? But also you have the motion field. The motion field, basically, we can just have, depends on how you can create the motion field. Then you can input the earlier algorithms or CNNs. You will input basically the data, each frame by frame, and then you input basically the motion field itself, right? As another input. There are some algorithms where just kind of try to handle that using LSTM or RNNs, where you can now get the motion information as you go from the time series. But just because the nature of the data, it has this axis about motion, it makes sense to put the pixels or the frames, and then you have the motion. So that's a pre-processing step, right? So it's really very, very broad to say what kind of pre-processing you can do or you cannot do. And it really depends on the application that you have. But specifically, if you really want to, only what you're focusing on is the features, then this is the whole point of having an end-to-end network. It will create the features, and then it will do the classification or the segmentation, whatever the application is, all at once, right? So everything is being learned in the training, right? So that's I would do that. And then so you can be creative. I will talk about the project later on, but you can be very creative. You can make the network create your features, and then do classification somewhere else, right? You can do that kind of engineering. Is it advisable? Is it really something that I would recommend? I don't know. It depends on what you get from this feature, and also where to stop. Right? Do you stop here and say that's my features? Do you stop here, or where do you stop to say well, that's my feature? Because if you look in here carefully, and this is something I will talk about when we talk about explainability and certainty after we finish CNN. Really, the feature generation is really happening here, right? This is where the features are being generated, right? The classification is happening here, right? This is basically narrowing down your feature space now from whatever dimension you have in here to 84 to 10, right? So you're really kind of, consolidating things together into 10 classes. So what you could imagine in here, basically you're creating all these spaces, all these representations or features. And this one here is trying to say, okay, now let me map these into 120 different, points on my hyperspace. And then this one will say, okay, now I will consolidate these from 120 to 84. And then the next one, I will consolidate these into 10 of them, right? So you can imagine that what's really happening is that you are really doing kind of almost like a clustering, more or less, right? You say, okay, this one belongs to this. And I'm trying to bring these together, and then I'm trying to make the different clusters away from each other. That's what the training is trying to do, right? So you can say, okay, I will get out from here. That's my features, right? You can do that, but that's a lot of engineering to do. It's not straightforward. Don't start doing that. Do a whole network first. Okay. So it was really kind of one of the first kind of CNN network that really worked end to end. Completely, it showed that it can learn features as well as do classification. And it also produced this kind of layout, which is actually proven to be kind of a de facto afterward. A convolution followed by activation, followed by pooling, and so on. And then you have fully connected layer at the end. So this kind of main contributions of this paper. So now, what are the pros and the cons in here? Is really a state-of-the-art performance at the time on the digit recognition task. You can see his presentation he and his students about when they demonstrated this. Basically, it was really kind of a big jump in the accuracy compared to other hand engineered method at the time. Nevertheless, it's really limited to grayscale images, very low resolution. I mean, the input is really 28 by 28 pixels, right? Images, so it's not really cannot handle really large images. It was robust to distortion and rotations, varying position and scale, so that was really a good contribution. And overall, people really tried the time for many different datasets, small datasets, great datasets, and it really worked very well throughout all the datasets. Nevertheless, it cannot really handle larger images or color images, and then it's really it requires quite a bit of computation at the time. This is 1998, right? So they started working on this 1995. Took them 3 years to get this out and running. So there was a big gap afterward. People really started to kind of engineer things, especially the hardware side of things, the GPU code algorithm, code language, and then creating data sets, right? Can we have data sets? And ImageNet basically came almost 10 years afterward into the picture. Okay, so the main work was really kind of get the optimization to work very well. What kind of impact we have if we have different initialization? What's happening if we have the gradient descent? Basically, is the only one we can do, or Newton second order representations, and then basically the vanishing gradient. So a lot of theoretical work took place in those 10 years. And then Alex came, and he basically literally, that's after his name, AlexNet. He was a PhD student at the time, and they came up with this kind of one of the most famous CNN networks out there, called AlexNet, and that was in 2012. And it's famous because it really won the ImageNet challenge at the time. So we have 1,000 different classes. We have 1 million data for training, and then I think 50,000 for testing. So he managed basically to show that basically this is work. So it's a lot of really trial and error throughout his PhD to get this to run. Eventually, Google bought his company and his advisor company after he graduated. But with this, the input, you can see the dimension is really large, much larger than what we had before. We have a convolution, we have a ReLU now, and then we have a pooling function. Then we repeat that again. And then now we have 3 convolution layers, each one followed by a ReLU. And then after the 3 layers, we have a pooling function. And then we have the fully connected layers throughout. And then we have here 1,000 because we have 1,000 classes for the ImageNet. Okay, so this is basically the first one that really showed ReLU as an activation to solve the vanishing gradient problem with sigmoid. So sigmoid and the hyperbolic tangent, they have the vanishing gradient. We talked about that last time, right? Remember when we said take the derivative, the Jacobian is small. Even if you have a big change in the input, you have the gradient will not change much. So the network will not shift to learn what's happening in the input, right? So he solved the problem because if you do lean it on ImageNet, will not really work much because of this problem. The network does not have a capacity enough to shift after the sigmoid. So ReLU basically, but there are some tricks he had to do to make this work, and we'll learn about 1 or 2 of them today. We'll learn about dropout. He really kind of the first one to show that dropout is really very important when you are training. He really ran this on a GPU, so fully 100% on the GPU. This is definitely much deeper and much wider than a LeanIt. You can see how many layers there, and then wider because the kernel size or the filter size are much bigger than a LeanIt. LeanIt was 3 by 3, this one 11 by 11, right? And then 5 by 5. So this is wider and deeper. So we have 1, 2, 3, 4, 5, 6 layers in here. So it's 1, 6, 7, 8, right? So we have 8 layers compared to 4 layers in LeanIt. Okay. He implemented, and we'll talk about this later on in the semester about data augmentation. Basically, he managed to make it more robust by adding data augmentation. Augmentation meaning, take an image, flip it, rotate it, different tricks. This in the augmentation with data. So the network becomes more robust. So he demonstrated that it can be done. And of course, he won the challenge for ImageNet